cutting practice, chapter 7, in the welding principles and practices book. Okay, this one's on flame cutting, and it is important that you learn the art of flame cutting before you're introduced to the various electric welding processes. It's really important to know how to cut when you start getting into the arc welding. Okay, the cutting of metals by oxyacetylene, oxyhydrogen, and oxyfuel gas processes is based on the fact that all metals oxidize to a greater or lesser degree, depending on the physical conditions around them. Okay, what this amounts to is it's an accelerated rusting process. After iron or steel is heated to a red heat and cooled, it's covered with a thick scale. These metals oxidize more rapidly when hot than when cold. If the temperature of the steel is raised even higher to a white heat and a stream of pure oxygen is directed against the white hot spot, it burns rapidly. This can be demonstrated in the shop by taking a thin piece of steel wire and heating it to a red heat and then submerging it in a vessel containing oxygen. The heated end will immediately burst into flame and burn vigorously. Okay, the reaction between oxygen and iron causes a considerable amount of heat. It forms a molten oxide that flows or is blown away, exposing more metal to the action of the oxygen. It's a chemical reaction. It's not a mechanical process that causes it to cut. The function of the cutting torch is to provide a flame, to heat the metal to the red hot state, to maintain that heat, and to direct the stream of oxygen onto the heated point for cutting. Practically all trouble in cutting is caused by cutting tips becoming burned or obstructed, or small particles of molten slag being entrapped in the orifices. Vertical cutting progression. Okay, anytime you're cutting in a vertical progression, always try and work from the bottom to the top. That allows the gravity to help remove the material. Okay, flame cutting effects on steel. Engineering investigation. A lot of people were, for a long time, afraid to use flame cutting if they were going to weld something. And because they thought that the flame cutting actually damaged the properties of the metal. And what they found was that when they started mechanically cutting the steel, whether with a mill or a saw or whatever, that the violent impact of the cutters or the blades on the steel actually did more damage than the flame cutting. They found out that it's better to flame cut and use those surfaces to weld on than to machine cut steels. Okay, a comparison of fuel gases. Function of the fuel gas is to feed the preheat flames that maintain the temperature of the materials being cut so that the cutting process can continue without interruption. Acetylene gas is the most common one used today. Okay, there are various other ones. Propane is one, MAP, natural gas, and propylene. MAP is a trade name for a particular kind of gas. Hydrogen was once used for underwater cutting because it could safely be compressed to high pressures and regulated to overcome the pressure exerted by the water at salvage operation depths. Natural gas, which can be similarly compressed, is now the most common for underwater cutting. Flame temperatures. Okay, acetylene burns 6,000 to 6,300 degrees Fahrenheit, I believe. It averages about 350 degrees hotter than MAP. Actually, acetylene is around 5,650. Okay, I'm sorry. I think it's 5,650 up to like 6,000, somewhere in there. MAP and propylene both run around 5,300, and propane and natural gas about 4,800. Acetylene burns much faster than the other gases, and therefore concentrates more heat in a small area. As far as the heat output, MAP actually burns with more BTUs than acetylene does. But because MAP doesn't burn as fast, it has a tendency to create what they call a bushy cone at the end of the tip, and it spreads the heat out more and doesn't concentrate it quite so much. And that's why acetylene actually generates more heat in a smaller area than MAP, because it burns a lot faster. Concentrates the heat a lot better. Acetylene is the highest priced probably of all of them, but it's the cost they consider to be offset because of the fact that it burns so much quicker. I mean, it generates so much more heat that it causes the operation to go faster. So for special applications, although acetylene has many advantages, no one gas can do everything the best. There are a number of applications for which propane and MAP gas, propylene, and natural gas may be better than acetylene. If you're cutting plates that are 6 inches or heavier, propane, propylene, or MAP are actually better than acetylene because a deep area must be heated, okay? The dispersed BTUs, or the bushy cone that I was talking about earlier, tend to disperse the heat better and cause it to heat deeper before it comes up to actual cutting temperature. And therefore those gases tend to work better on really, really thick steel. As far as cutting different metals, oxyfuel cutting finds its widest use in the cutting of carbon and low alloy steels. The normal oxygen cutting methods must be varied for metals with high alloy content such as titanium, cast iron, and stainless steel. Some of those things are really difficult to cut with oxyacetylene. Generally, as the amounts of alloying materials, including carbon, increase, the oxidation rate decreases. This is one reason why cast iron, which has a high carbon content, is more difficult to cut than carbon steel, just low carbon steel. Preheating. It's been pointed out that high heat increases the rate of oxidation. As a consequence, many materials that are difficult to cut can be cut more easily if they are heated to a temperature approaching their melting point. Okay? All right, when the torches move from side to side, more material is heated to the ignition temperature so that additional material is oxidized and blown out of the kerf. This is one method used in the cutting of cast iron and produces a rough cut. But because you're spreading the heat more, generating a wider kerf, it makes it a little easier to cut cast iron. Welders must manipulate the torch when cutting so that they create the proper kerf and drag for the material being cut. The kerf is the gap created between the material as the material is removed by the cutting process. Okay, the groove that's cut between the plates, that's known as the kerf. The width of the kerf is determined by the size of the cutting tip, the speed of cutting, oxygen pressure, and torch movement. Since oxygen pressure is directly affected by the thickness of the material being cut, the width of the kerf increases as the thickness of the material increases. So if you're cutting, 2-inch plate, your kerf's going to be a lot wider, so you're going to have to allow for more loss of material than if you're cutting, say, 1/4-inch plate. Okay, drag. When steel is cut, lines form on the face of the work that are caused by the flow of the high-pressure oxygen. When the torch is held in a vertical position and the cutting conditions are correct, this line is vertical from top to bottom. This condition is referred to as zero drag. If the speed of the cutting is increased, or if the oxygen pressure is not set high enough for the thickness of the material being cut, the drag lines at the bottom of the kerf lag behind the top of the kerf. In reverse drag, the drag lines at the top of the kerf lag behind those at the bottom. Reverse drag may result from too much oxygen or a speed of travel that is too slow. Okay? All right, straight line cutting. A lot of times people, if they need to cut a straight line, they'll use some sort of a magnetic square or a fixture of some kind that more or less sits on the plate, and then you just butt the torch up against it, drag it along, helps you keep a nice straight line. Bevel cutting is a common practice. It's used in beveling the edges of plate and pipe for welding. Okay, and it simply the torch is laid over at an angle so that the cut is made at a beveled angle. If you're hand beveling, that's kind of a difficult process to do. It takes a little bit of practice, and you'll get some practice at it in the shop. But it's getting the restarts right and things like that. That's the problems that come along with the hand beveling part. The best way to flame bevel something, like if you're doing a pipe, is to use they have a hand crank flame beveler that the torch is actually tilted over at an angle. It's got a series of gears and chains and stuff, and it just cranks the torch around the pipe at the same angle the whole way. It makes really smooth bevel cuts on pipe. And if you're bevel cutting plate, the best way to do it's on the track burner. Just simply set the torch at whatever angle. In our case, it's usually 37.5 degrees. Just let it run along there. It makes a really nice clean cut. Okay, piercing. Piercing is the process of forming a hole in the metal part, maybe for the purpose of producing a bolt hole or starting a cut from the edge of a plate. Okay, in other words, cutting a hole in it. What it amounts to is holding the torch in the center of the hole until you get the red hot cherry red spot in the middle. Back the torch up slightly, start the oxygen kind of at a slow rate on the cutting lever, let it start piercing down through. A lot of times you get a spray of sparks out of there. Once the thing is pierced through, then you can travel out to the edge of the hole and just make your circle. Scarfing and washing, pretty much the same kind of thing. A lot of times they're done with a special tip with a curved nose on it so that it can lay down flat on a plate. They're used for washing or scarfing off rivet heads or anything that may be standing up on the plate that you want cleaned off without actually damaging the plate. When you get into groove plate welding and you start doing filling 3/8 plates with a backing strip, before those coupons can be cut out and tested in there, the backing strip has to be scarfed off. And that's one place where you'll really start learning about scarfing. Okay, flame gouging. Okay, that provides a means for quick and accurately removing a narrow strip of surface metal from steel plate, forgings, or castings without penetrating through the entire thickness of the metal. It's generally used for removal of weld defects, tack welds, metal from the backside of a weld seam. A lot of times things may have to be back welded, which means you go in and you gouge out the root pass and refill it with good weld metal on the backside. It's done by laying the tip over at a very, very, very flat angle and just starting real slow, bringing the tip up very slowly and gouging out a groove into the surface of the plate. Okay, the surface appearance of a high quality cut. Since one of the principal fields for oxy-fuel flame cutting is in the preparation of plate and pipe for welded fabrications, it is important that the cuts be accurate, smooth, and free of slag that will contaminate the weld or cause the welder to spend a great deal of time in grinding or chipping. Okay? A correctly made cut, the edge should be square, the drag lines should be vertical and not too pronounced. You see some pictures on the next page, page 212 in your book, of some cuts and what they kind of show you what is proper and what is improper as far as the way they look. Conditions that affect the quality of the cut. Okay, this is a list of important conditions that should be met in order to make accurate, smooth cuts. Uniformity of oxygen pressure regulation. Okay, make sure that you got good equipment, good regulators, stuff like that. Keep a good, steady oxygen flow. High oxygen purity. If the oxygen contains impurities, the chemical reaction that takes place in the cutting operation will produce poor quality cuts. That goes back to your gas supplier right there. Proper oxygen operating pressures. Okay, make sure, and you'll see charts all the time, like on our cutting table we have a chart that tells what oxygen pressure you should be running for what thickness of plate with what tip size. So make sure you pay attention to that because it'll certainly help. Proper tip size is the next one. That's the same thing. And always make sure that the tips are clean. Clean out all of the preheat orifices, clean out the oxygen port all the time, and it has to be done on a fairly regular basis too. Smoothness of bore and proper cutting orifice. Yeah, make sure that they're clean and make sure the preheat orifices are clean. Uniformity of the steel being cut. Any variation in the thickness of the material, its shape, or the plate surface condition alters the cutting procedure. Low enough speeds for light and moderate thicknesses. A common error is to proceed at an excessive speed, which results in a cut of poor quality. a gradual increase in speed when starting the cut in very heavy thickness, okay? High enough speeds for heavier thicknesses. If the speed is not high enough, the lower portion of the cut will be ragged. To increase the speed, it is necessary to increase the tip size. So in other words, if you're having to go really slow to get through and it's causing a poor quality cut, you need to go up a size so that you can speed up a little bit. Okay, cutting thin material. Angle the torch toward the direction of cut to prevent the material from wanting to fuse itself back together. It's a problem. Anytime you get below about 3/16 inch plate, you have to really put a steep angle toward the direction that you're traveling on the tip, or it simply just fuses right back in behind you as you're going. Talk a little bit about arc cutting here. In the large welding and fabricating shops, there's a growing use for the various arc cutting processes in the fabrication of heavy weldments of various kinds. Okay, you'll get more into this in a different chapter as far as plasma arc and air arc gouging and stuff like that, so we won't spend a lot of time on it here. Setting up and closing down equipment. Okay, the following equipment is what you'll need for oxyacetylene cutting. Okay, a fuel gas cylinder, oxygen cylinder, oxygen regulator, fuel regulator, oxygen hose, fuel hose, cutting torch with cutting tip, cutting goggles, fuel tank wrench. There's different kinds of fuel tanks. Some of them do take a wrench or a T-handle to open and close. Torch wrench and friction lighter. Okay, the torches we use, the only thing you need a wrench for is installing the hoses on them. The cutting head and probably the tip. The cutting head goes on just hand tight. All right, the following manner is how the equipment should be set up. Dirt and dust sometimes will settle in the valves, in the valve seats and stuff like that. So the first thing you want to do is take the bottles and just crack them open a little and let a little bit of gas escape, and it blows that dirt and dust out of the inside of the valves, okay? Then you need to attach the regulators. Oxygen regulator, okay, remember it has right-hand threads. Then the acetylene regulator, and it has left-hand threads. Okay, you'll tighten attach the hoses next, tighten the nuts. Remember that the acetylene nuts are on, or acetylene hose is red. It has the nuts with the groove cut in the flats. Oxygen hose is right-hand threads, and it is green. Make sure all of that stuff is tight. Attach the backflash arresters to the hoses and then to the torches. Make sure all of that stuff is tight. And at that point, you should actually back your regulator screws off in the regulators, turn the bottles on, bring the regulators up to working pressure. For acetylene, it'll be 5 to 7 psi. For the oxygen, probably in the neighborhood of 35 to 40 psi. And then go and check all your fittings so you make sure that you have no leaks anywhere in the system. Let's see what we have next. Okay, you want to, once you get everything on there, you'll attach your cutting head. Like I said, the cutting head only goes on hand tight. Make sure that the cutting tip is in the cutting head, and it has to be tightened down with a wrench so you don't get any leakage around that. Then you'll open up your acetylene valve, just a crack, maybe 1/16 or 1/8 of a turn. Strike it with a spark lighter. You'll notice the flame has a lot of black soot in it. You turn up the acetylene until that black soot clears. Once that soot clears out, then you can start turning on the oxygen. You bring it down. There's a inner cone, and then there's a secondary cone or feather inside that, and you'll watch that as you bring the oxygen up. That feather will slowly go down towards that inner cone. When it just blends in to that inner cone, that's when you're burning a neutral flame. That means you're burning equal parts oxygen and acetylene at that time, and that's the most desirable flame for just about everything that you'll be doing. Okay, if you overdo the acetylene, you end up with what they call a carburizing flame, where you're burning more acetylene than oxygen. If you overdo the oxygen, then you're using an oxidizing flame, which is burning more oxygen than acetylene. Okay, practice adjusting that flame several times until you really get familiar with what a neutral flame is, okay? Once you get that down there, you want to check your preheat flame to make sure it's neutral, because as you add your cutting gas, it will actually go to something of a carburizing flame. So you want to hit the cutting oxygen lever and watch the inner cones at the preheat nozzle, and if they stretch out and get a little bit longer or fuzzier, then go ahead and adjust your oxygen up a little bit more until those cones clean up, so that you make sure you've got a good neutral flame. Okay, then you want to hold the torch right down to the material within about 1/8 of an inch, 1/16 to 1/8 of an inch of the material, until you get the cherry red spot, really bright red, hot, and then once it gets heated up on the edge, and you just go ahead and mash the oxygen lever all the way down, and the cutting process will start. Okay, closing down the equipment. Okay, once you're finished, what you'll do is you'll go ahead and you'll shut off the valves on the torch. Shut off the acetylene valve first, the flame will go out, then shut off the oxygen valve. Then you'll shut off your regulator valves. And once you've done that, then you can go ahead and open up the valves on the torch again, let the whole system bleed out. You can watch the needles on the gauges on the regulators, and they'll just drop down to 0. Once they get to 0, that means the system has bled completely out. Okay, and then you can start disassembling everything. Make sure when you're done, you put all the caps back on the bottles after you get the regulators off. Just a few terms here real quick that describe the surface of an oxy-fuel cut quality, just some terms that you might want to know. Flatness. Flatness is the distance between the two closest parallel planes between which all points of the cut surface lie. Okay? Angularity, that's the deviation in degrees at any point that the cut surface from the specified angle. Okay? In other words, does it wander back and forth like that? Different angles. Drag lines, those are the lines that appear on the oxygen cut surface. Their contour and direction do not affect the quality of the cut surface. Okay. Roughness. Roughness consists of recurring peaks and valleys in the oxygen cut surface. It can be determined by samples of acceptable quality or by comparison to the AWSC 4.1 Surface Roughness Guide. Okay. Top edge rounding, that's the melting of the top edge of an oxygen cut surface. Notch are gouges in an oxygen cut surface significantly deeper than the overall surface roughness. Slag. Slag is a deposit resulting from the oxygen cutting process that adheres to the base metal or cut surface. All right. I think that's everything in this chapter that we'll be going over. So make sure you read everything carefully, and good luck on the test.